Hello everyone, my name is Ian. I'm going to be presenting the 8th place solution to the SIIM ACR pneumothorax segmentation challenge hosted on Kaggle. Our team was composed of myself and my teammate Felipe Kitamura. I'm a fourth-year medical student at Brown University going into radiology. I've had prior experiences with radiology machine learning competitions. Felipe is the head of artificial intelligence at Dataset, which is a Brazilian diagnostics company, and he's also a clinical neuroradiologist in Brazil. He also had experience with previous radiology machine learning challenges, which is how we got to know each other. This competition can be broken down into two tasks: binary classification of chest radiographs into pneumothorax versus no pneumothorax, and segmentation of the pneumothorax region. The metric was the dice similarity coefficient. Notably, true negatives were given a dice score of 1, which penalizes false positives much more than false negatives. This competition took place over 2 months, and it was a 2-stage competition. The training set for Stage 1 had over 10,000 images. The Stage 1 test set, about 1,300 images. The Stage 2 test set contained 3,200 images. The prevalence of pneumothorax was similar across these three datasets. This makes it easier for models and prediction thresholds to generalize across datasets. The images were obtained from the public NIH Test X-ray 14 dataset, 8-bit grayscale images downsampled to 1024 by 1024 pixels. 10% of our training data was used as holdout for testing ensembles. The remaining 90% were divided into 10 folds. All folds were stratified by pneumothorax size. We used the DeepLab B3 plus segmentation architecture developed by Google with ResNet and ResNext encoders that were pre-trained on ImageNet and used group normalization instead of batch normalization. We thought that this would help improve performance at lower batch sizes. DeepLab B3 Plus uses an encoder-decoder structure and atlas or dilated convolutions to increase the receptive field for better segmentation accuracy. We trained our models in Python 3 using PyTorch. We had an NVIDIA Titan V100 32 gigabytes and a Titan V 12 gigabytes. For our learning rate schedule, we used cosine annealing with warm restarts, which means that at the end of every cycle, we will restart the learning rate to the initial learning rate. We trained for 100 epochs and 5 snapshots or cycles. We used stochastic gradient descent with momentum, initial learning rate 1 times 10 to the negative 2 to 1 times 10 to the negative 4. Each model was actually a snapshot ensemble with the 3 best snapshots based on the validation competition metric. 2 types of models were trained: joint classification and segmentation models, and segmentation-only models. For joint segmentation classification models, we wanted to train one model that could both segment out the pneumothorax region as well as classify images into pneumothorax and no pneumothorax. We used a batch size of 4, gradient accumulation of 4 for an effective batch size of 16. These models were trained on all images, original distribution, weighted binary cross-entropy loss. Resolution was 1024 by 1024 and 960 by 960. For segmentation-only models, the goal was to get better segmentation precision, so we trained on positive image only with a soft dice loss. We used a batch size of 1, gradient accumulation of 16, 1280 by 1280 resolution, and 1024 by 1024 resolution. This is the inference pipeline that we used. SC represents joint classification and segmentation models, and S represents segmentation-only models. So we had 4 joint models, and we used 4 of these models to just classify images. So we used the top pixel score as a classification score, and then multiplied that classification score into the prediction masks from the segmentation-only models. In this way, we could combat the increased number of false positives that you get with the segmentation-only models. And then we have 4 other joint classification segmentation models where we just take their predictions as is, and we average all of these together to get our segmentation masks. We apply our classification threshold, and then use a lower segmentation threshold for those images that met the classification threshold. And finally, we use a size removal threshold to get rid of small masks. And because the metric penalizes false positives more than false negatives, we found that this was very beneficial in improving our performance. Our final scores on the stage 1 test set were 0.878 with the size removal threshold of 4,096 pixels and 0.8768 using 2048 pixels. For stage 2, we submitted 2 solutions with the same size removal thresholds as in stage 1, and we found that 2048 pixels actually did better, the score of 0.8627. This was our final score for the competition. Takeaways from this competition: the segmentation labels definitely helped improve classification as well. We tried training classification models without segmentation labels, which performed worse, and upon examining these predictions, we found that a lot of times they were detecting pneumothoraces, but really it was just detecting the chest tubes in the image. High resolution was better than low resolution in our experiments. Group normalization helped with our lower batch sizes, and we exploited the metric with the size removal threshold, which helped us get rid of any false positives from small masks. And we found that finding the right loss function is really important. This competition saw a wide range of loss functions being used. We had the most success with a weighted binary cross entropy loss when we were training on all images. And it seems like teams use combinations of binary cross entropy and dice losses in their models. Thank you very much to the hosts and the organizers for allowing us the opportunity to compete. Feel free to contact us with any questions.